Okay, so welcome everybody. It's an honor for me to introduce Caterina Taballione. And yeah, we met a few weeks ago when we had another seminar where you introduced Quix, your company, but the products of it. And today you're telling us the history, how Quix got created.
Yeah.
So please.
Yeah, thanks, Florian, for the introduction. So good morning, everyone. My name is Caterina Taballione. I'm from Quix Quantum, and I'm a senior quantum engineer at the company. And so today we were asked to come here to your spring school and to talk about the history of Quix Quantum. You might not have heard about it, of the company itself, but today I would like to let you know and tell you this story because it's really how everything began. And maybe that can be the same for you in the future, who knows? Huh? I hope you have some energy left from yesterday. I kept it light, so this won't be full of, this presentation won't be full of formulas and graphs. So hopefully you'll stay awake, but please, this can be an interactive lecture, so it's light and it should be fun. So I hope for you. So please ask questions also whenever you want, basically. So let's have a look. We have an hour. We have started a bit later, but I guess we can still use more or less 1 hour. And yeah, I thought of dividing the next hour that we'll spend together, let's say, in 3 branches. So first of all, I will tell you the story of Quix and how I would have never thought that my PhD will turn into a business, honestly. And then second, I thought, okay, we can, play some game in which maybe we can use, our soft skills, and you get to know how it is really to be in a company. And then, well, sometimes left for questions that you might want to ask of any sort. So let's start. I would have never thought it would turn into a business and how Quix Quantum was created. Now, before going into that, I just want to tell you a bit what we do now, right? So what is the technology we work on and who we are as a company. So what is our mission? To make the world's best quantum photonic hardware. Now, this is a picture of a real system that we manufacture. That is a wafer size integrated photonic chip. Now, how many of you are familiar with integrated photonics? Okay, I see very few hands. Very good. Okay, so then we'll see something more afterwards, but who is familiar with photonics? Optics, a lot of you, right? Okay, you are familiar with big lasers, true? With bulk optics, correct? With wave plates, with detectors and all sorts of equipment, right? And what is the most difficult thing that you encounter, for example, if you have to name something? When you deal with optical system? Alignment, very good. Something else? I mean, alignment, just mechanical drifting, but yeah, something kind of similar to alignment. Stability, right? Phase stability. That's also another problem. When you have optical signals interfering, then any drift in the ambient temperature or in the change of a material while the light is propagating through, that changes your phase stability, right? That changes the refractive index of the material, and then the phase of light is changing. Okay, very good. All these problems are fixed by integrated photonics. So what you see here, it's a zoom-in picture of something that it's, well, more or less like this, of this size. And it's just a piece of glass that looks a bit dark. So you have some materials layered on top of each other. And let's say in the thickness of this piece of glass, there are some waveguides. And you might have heard of this name, but well, if you just break it down, waveguides. So are structures that guides optical waves, okay? And you can basically have what you would need on an optical table that it's maybe even bigger than that, with bulk optics and beam splitter, phase shifter, fibers, you know, and that you go there in the lab every morning and you just pray God that this time will work. Well, on a tiny chip, on something like that, integrated photonics, the structure is fixed and you get for free phase stability and well, let's say alignment forever. We use this technology. Okay, so if you're not familiar, I can tell you whatever material it is, you don't care. But let's say the material we use has excellent qualities for being used in quantum optics. So right now we are a team of 12 people coming from various backgrounds: quantum optics, integrated photonics, software engineering. And we are all together working in reaching, you know, our goal. Now, we are a market leader in photonic quantum computing hardware. Okay, now maybe another question. Have you heard about quantum computing, right? Okay, so can you tell what are the advantages of quantum computing? Yes. That's, let's say, the most, yeah, okay. And do you know, let's say like this, do you know what technologies are out there to build a quantum computer? Very good. Yes, you probably have heard of Google, right? Superconducting quantum computer, showing a quantum advantage. Very good. Well, you probably haven't heard that also photonics, a photonic quantum computer reached quantum advantage. And this is the paper that where the results have been published. So photonics is the only other quantum technology that succeeded in demonstrating a quantum advantage. As Google, on a very specific algorithm. Yes, question, tell me. This was about 100 Q modes. That's, let's say, the optical parallel of qubits somehow. There's a bit of translation there that needs to happen. And so there is, photonics is, what do I have to do? Okay, yeah, Florian will do that. So photonics is one of the only two technology platforms that succeeded in demonstrating a quantum advantage. And this was demonstrated in China. And this is the picture of the experimental setup. Now, I don't know if you can see it, but it looks pretty crowded, right? All these are beam splitters. All these are fiber coupled, fiber cover, wave plates, lenses, whole source of bulk optics material. This is what we call a multi-mode interferometer. So you have many input light beams that are divided and that they are recombined, let's say. And then in this recombination, you apply some relative phase delay so that you can, and these phase delays that you implement are basically your input for the encoding of your problem, just to give you a simplified picture. Now, this is a hell of a job to keep it running. That experimental setup, you know, I just have goosebumps, just like, ooh, it's a nightmare. You need active phase stabilization, active loops to keep the whole system phase stable, and a huge number of PhD students to run it, basically. How do you make this thing scalable? How do you make this thing sustainable and programmable? So also another important thing, if you have a setup, right? You have a beam splitter, okay, a polarization beam splitter or whatever, or a wave plate or something. You want to change, you know, your setup. You have to go in there and manually, I don't know, rotate your wave plate or take out your 50-50 beam splitter and put one of 90-10 or something like that. And then what you have to do is to realign and wait that the whole system goes back to stability. So this is the same. This is not programmable. You cannot change it on the fly. How do you do that? With integrated photonics. And this is what we do, basically. We make this big system on the chip, on a chip, like the one that I've shown you. And so going back, actually, this is what we do is basically we take this tiny chip, we build the whole system around, like you see it here. So here, very small, there is the chip. These are, you might recognize it, are just some fibers. It's a bundle of fibers or fiber array that are glued to your chip. Here there is some electronics around to control your chip. Underneath, there is a whole bunch of power supply, cooling system, and so on. And then basically you put the cover on top and you have a one rack metallic box that you can bring around. And this is what we call a quantum photonic processor. That if you think about a quantum computer, you have some quantum light sources, you have your processor, and you have then your detectors. And the processor is the central piece of this whole system. And now, the advantages of photonics are over, for example, superconducting qubits or other type of technologies are, just to name a few, the low decoherence. So single photons do not interact. They don't have mass. They are not affected by external electromagnetic fields. They operate at room temperature, the processing of it. And then there is a strong technology crossover with classical photonics. So integrated photonics was not born for quantum, not at all. It's biosensing, telecommunication. But we can take all the technology that has been developed and transfer it into quantum. And we do that because the integrated photonics technology that we have, it's really good for quantum because of the low loss. And now just to give you an idea how a quantum computer works with photons, it's basically you have a set of rails that are your waveguides, and you have some switches so that you can, link at certain points your rails or your waveguides so that your light that it's in here or in there or on both start interacting and building up entanglement. That is what you need for quantum computation. And the point is that in integrated photonics, we can program these switches to, switch on and off how we want. And the computational power is set by the number of these rails or how we call it modes. There's more or less like qubits. And then you can do machine learning, optimization problems, and quantum chemistry. Yeah. No, that's one chip for all. So that's the point, that it's fully programmable. You have a big mesh of all your switches and all your rails, and then you can program all these switches to, I don't know, be a certain circuit, and then you switch them back to be another circuit, and so on. So it's where the programmable comes from. And so we have, well, in March this year, we have demonstrated the world's most powerful quantum photonic processor. Here you see a picture. So this is a 1.5 times 2 centimeter chip. Here you see some fiber array. So there are some just bare fibers in here on a V groove, just glued together and stick to the chip. Some electronics connected to the chip. And well, we build the system around it. So that's our, what I called a metallic case around it, where you have some fiber connectors at the front panel, and at the back, just a USB plug. You can connect your PC and then program your processor for what you want to do, for any, I don't know, quantum gate or quantum computation. And this is like a screenshot of the software interface that you would see. So it's via Python, and that looks very slow, okay? Where, you know, you just call our library, and then you say, okay, you know what, let's just do, for example, an identity matrix. Now, just to show you the easiest case. And there, then this software translates the commands as to the actual hardware setting of the processor, and then you get the measurement done, for example. And the idea, so the plan is by the end of next year, we will put the system in the cloud. You know, maybe the IBM system, Qiskit, you can access it via web, where you can just go there and program your experiment. And well, that's basically the same. It will be via Python, and you will have the full control of the equipment. So the processor, the sources, and the detectors. And well, we had already some quite nice outputs from our collaborators, where they could do actual science, you know, actual quantum experiments with our system. And for example, to give you an idea what our collaborators and also customers like, and why what we do, it's important, it's a key enabling technology, is that experiments that would take days or weeks, now it takes just a few hours. So it means that who does quantum optics really on research level, quantum algorithms, now have a device that works, you know, that makes it possible for them to progress in their research. This, I think it's very cool. And now the scientific part is over. If you have questions, please go ahead. But you can ask them whenever you want. And now we go to how everything started. So now it's 2022, right? So it's been quite some years, 7 years. It was 2015. I was just graduated from Rome, my master's, and I was like, oh, what should I do? I don't know, let's see. Maybe I go to work in a company. But at that time, so I did my master in Rome in quantum optics. At that time, quantum optics, was like, what? What are you talking about? So there were very few people doing this. There was just, I think, ID Quantique at the very beginning of their company building. And then I said, okay, I'm just gonna do a PhD in the Netherlands. Oh, it seems fun, in integrated photonics. Cool, okay. And then I moved to Enschede. There's a small town in the Netherlands, close to the German border. Now, 8 hours away, so how many kilometers? 738 kilometers away, Jelmer Reinema, that's our current CTO of the company, was instead doing his postdoc in Oxford, in the group of Ian Walmsley. That's quite a famous group for quantum optics, quantum information processing and quantum optics. And, you know, they had great minds, great ideas. Oh, let's be the quantum memory or a quantum processor, quantum processing. Maybe we should do this gate, the teleportation scheme and whatsoever. But that was just on an optical table. And, you know, it was never working. And, oh, now this piece has broken. Oh, now this work and oops, now this other one is broken. So, you know, it was great ideas, no devices. On the other side, we were building devices, but having not the theoretical background. So builders and thinkers. And now what happened is that one day, Jelmer got invited by the University of Twente to give a talk. Because the University of Twente, there is in Enschede, there was, you know, they wanted to start a quantum optics group. So they invited him. And him, by the way, is Dutch. So that kind of makes sense. And so he came over at the University of Twente. And, you know, I was just a PhD student in my mid-PhD crisis. So I was halfway of my PhD. And I was like, yeah, okay, but this project, I don't know if I like it or not. And then this, you know, this guy came over and he was like, well, you know, we have a lot of knowledge in quantum optics. We have great ideas, but then the experiments never work. We cannot go on. And he was like, well, I know you guys make a lot of good chips. Maybe, you know, do you have something like that we can use? And at that time, to make you understand how strong it was the hardware effort in our university, I made a book that was tall like this with the inventory of all the chips that we had lying on the shelves. And I was like, wait, I know, come here. I took this book and I opened it, and then we went through every page, like, let's see, this one can be useful. No, maybe not. You know, these are rings. No, we need something different and so on. So going through the books, then we found nothing. So he came with a great idea and we found nothing. And I was like, damn, that's not nice. There should be something. And then discussing with him, was like, yeah, but you know what we really need? We basically need an interferometer, a Mach-Zehnder interferometer that's on chip that I can, you know, tune the phase of one of the two interferometers arms. And then I was like, wait, I have it. There was one chip lying on the shelves, and it's that chip there that was fabricated 2 years before Jelmer came for something totally different. There was microwave photonics, optical beamforming network, how to steer, you know, the phase front of a bunch of antennas in different directions. And what you actually need to do that, it's basically a multimode interferometer with tunable phase delays. And that was exactly what it was needed for quantum information processing experiment. And then what happened is that, okay, let's do it. I come to Oxford, and then I took my car, which is just a toy, Ferrari, by the way, a Lamborghini actually. I packed, literally, I'm not kidding, I packed that chip, put it at the back seat of the car, and with a long drive of 8 hours, I was in Oxford. And then from that moment, so there was a young myself many years ago, and very excited to start this collaboration. And well, Oxford was nice, Trinity College, and you know, some squirrels, so some wild animals lying around, scones and tea, and nice cakes, English breakfast. So there was great time, but you know, it was constant measuring every day from morning till evening, every day, because we wanted to work. And after quite some months of measurements, because of course the source was down, the detectors, the cryostat of the detectors was not working, but it took a while, well, 4 months, which is not that long anyway, but we got the results we wanted. And this was the first coincidence measurement that we made on our chip that was like, you know, green flag. Yay, it's working. So that has a special place in my heart, that graph, although it looks not that nice, but anyway. And then from all the work that we have done, so we could, you know, implement quantum gates, quantum transformation, quantum interference, and then this whole was then collected in a nice paper where we also showed that the platform that we use, so the material that we use, is basically offers is the most scalable. It's with that material, it's possible to make the quantum photonic processors largest of all, the largest processor of all. So that was quite nice. And now I don't remember what comes next, so sorry. Okay, but now I was very, you know, very excited. I got the results for my PhD. And this was like, okay, Caterina, you can graduate. But now, okay, I was done with my homework, right? And well, to be honest, I have to tell you, at that time, I was quite young and innocent, and I would have never, ever thought that what I was doing could turn into a business. Never. Even if someone from the future would have told me, would come and tell me, hey, this is going to be a big company. No, no, not at all. Now, I don't know if you're maybe too young to remember this movie, but that's basically, and yeah, okay, there was a famous movie when I was a teenager, that tells you, you know, this butterfly effect. You take a decision and something happens. What if you would have taken another decision, for example? A totally different reality would come. And let's say you have to be at the right moment and at the right place. If you are at the right place, but you are not at the right moment, you might be too early or too late. And you are not ready to really see the potential of what you are doing. Or as well, it's the good timing for you, but you are not at the right place. So then you actually don't have, you know, the technology maybe that you want, or the collaborators that you want. So for me, that was like, I had no idea. I was really naive at that time. Fortunately, Yelmer, that was talking about right timing, that was ahead in his career. You know, he was older than me in his career in that sense, did. So he saw the potential. he saw an opening in the market for quantum photonic. And so a startup was born, January 2019 in Enschede with this one. And now, so far, this works. So that's our logo right now, Quix Quantum, which it's kind of nice. But so January 2019, Quix was founded. And in July 2019, I got my PhD degree. So yay, congratulations. And well, basically all the work that I did in Oxford and that led to Quix was basically, republished in my PhD thesis. That's actually the cover. And that's a hand drawing. So you can see that I had quite some free time in the end to even draw my cover. But anyway, so that was nice. But in April 2019, even before graduating, I started working at Quix as patient zero. No, I was employee number 0. So it was, very excited. Yay, it's business, yeah. And that was just me and myself. Okay, and Jelmer, that was, working also at the university. So there was quite some stuff to do and to arrange at the beginning, bringing forward the research, the actual research in the lab, but also do everything else. And, when corporate life starts as a startup, one thing is if you go, I don't know, to work for Philips or, I don't know, Google, that's already, all set. It's already started. But when you really have to start, well, you start with this, right, in your mind, formulas, and the technology, the science. Yeah, that's not all. So you need to be ready, right? There are a lot of many things that you have to do. Setting up your facilities, right? Your office, which, there was an animation that, well, but anyway, for example, I don't know, release some interviews and be on the newspaper, right? So do some shooting, do some scientific talks, webinars. That's a screenshot from one of our from our first actually product release. You have to then, learn how to ship your products to customers. And these are the 2 crates where inside there was the processor, so the thing that I've shown you, and all other optical equipment that we ship to the customer. You need to do remote installation, for example, with your customers, so that they can work with the system that you provide. You maybe have to do, that's maybe fun, some videos and some interviews for promoting your company. That's very important as well. And well, maybe you also have to be the presenter for like of a TV show or something like that. So I have to say, it's an exciting life for ambitious people. It's not only science, is really the base. It's really where everything is built up. And then to really grow, well, actually you need all these sorts of soft skills. And well, yeah, the soft skills, are of any sorts. That can be communication, because I don't know how is your PhD, right? But mine was, okay, you have your project. It's part of a big, for my PhD was Memphis 2. It was this huge call across the Netherlands with many, many different projects, but you have your own task, you do your own research, and it's you in the lab doing the measurement, doing the analysis, preparing the presentation. Then you go to this meeting with the user committee meeting. Maybe you have something similar. And well, you talk with your supervisor, with your professor, sometimes with your colleague in the lab. Hey, how do you think I can improve this, what it works or what not? But in a company, really, you really, and in a startup especially, you have to grow fast, and you have to be strong, both in technology and in all the rest. And so communication, it's very important with your colleague, or even if you are maybe a senior level, that you have a small team to lead and to organize. That's also very important. You know, we are all scientists. We all know what we would want to do, what, you know, we think it's best. And then, so it's communication, it's very important. Negotiation is very important. Management skills. And of course, well, time management and organization, that as well. So there are all sorts of skills that you need. And I guess also during this spring school, you guys have had some sort of lectures on this or something. Is that correct? Yeah. What did you do? What topics you had? Yeah. How to? Yeah. Yeah. Good. Okay. So then that's perfect, because these are two topics that are very important: how to work in a team. So that's communication, negotiation. How do you convince me that your idea, maybe it's better, right? Without being too pushy. I'm talking to you not just because you made the example, I am sorry. You know, or maybe, yeah, knowing your personality, your color. There are, I guess they explained to you, there are different type of personalities, different type of colors. And, you know, that can, figuring out what color a person is, can help you in, you know, in the negotiation, in the communication.